Hello and welcome to Engineering 246, Mechanics of Materials. This is Professor Lin, and this is our very first lecture. Let me start off by apologizing for having to rely on these video recordings. I do have a family situation that requires me to be out of the country until February. So, as you've probably read from my Blackboard posting, we will be conducting the first few weeks of the class via this online format, and we'll try to make this as painless as possible. All right, now some preliminaries before we actually get into a lecture. I have mentioned that there were notes posted up on Blackboard. So for those of you that haven't taken a look at those notes yet, please go ahead and log onto Blackboard and read through the announcement that I have posted up. Okay, there's some important notes that I wanted you to be aware of, and there's also the contact information for Professor Woodkey and Ms. Rucker if you have any problems with this course that need to be handled, and which I'm not able to take care of since I'm out of the country. Okay, the next thing is the syllabus. Okay, and that's already posted up on Blackboard as well. So if you go to the correct link, you should be able to bring it up. Right? Perhaps print out a copy for yourself. And I would highly suggest that you go through the syllabus, right? And that's always important because there's usually a lot of information that's contained in syllabi. All right, so let me just point out a few things here, right? Obviously, my contact info, office hours for once I return, and all of that, that's all up on the syllabus. The textbook, okay, is the one by Beer, Johnston, DeWolf, and Mazurek. The latest edition, I believe, is 8th, all right, and it might even be the 9th. The note about the textbook here is that you can use any edition that you would like. Okay, I've actually been using the 5th edition for quite some time now, and I'm pretty much going to stick to that as far as problems that I post up solutions to. Okay, so you'll notice on Blackboard there are, under course documents, some problems that I've posted up. Okay, and you'll see that they're all from the 5th edition, so I've posted up solutions that I've worked out from some select problems. These are problems that I feel are a good representation of the material that's covered. Okay, for those of you that are not using the 5th edition, right, that's not going to be a problem because you can see that I've also posted up scans of all the problems out of the 5th edition. Okay, so use these as a resource. Let me point out that there are some errors in my solutions, but if you ever encounter anything that doesn't make sense, feel free to contact me. All right, come into my office hours or email me. All right, so that's the syllabi. Now let me go back to, those are the problems. Let me go back to the syllabus. Right, and let me repeat that as far as the textbook goes, you can use any edition that you would like. All right, now, let me scroll through the rest of the syllabus here. The other important things on the syllabus, okay, let me just go over it real quickly. Obviously, there's a course outline. Right? You can see all the dates that are listed and the different topics that we're going to be covering during those days. Okay, so you could look through that. That'll give you an idea of what we'll be covering and when we will be covering those topics. Excuse me here. All right. You also see on this syllabus that there are 4 exams, okay, that are going to be given as part of this class. And because I'm going to be out the first 3 or 4 weeks, okay, I'm going to hold off on the first exam until I return. Okay, and that's tentatively February 15th. Okay, that's going to be our first in-person meeting. And on that date, I will give you your first exam. It will be a take-home exam. Okay, you'll just give that back to me or turn it in to me the very next class on February 22nd. Okay, and then the week after that will be exam 2. That's actually going to be in class. Okay, just like the remainder of the exams. All right, so look through that schedule. Also on the syllabus is your grading. Okay, we'll get more into that once I return. Okay, I don't want to spend time on that now. All right, and then there are also some important policies and notes. All right, so again, read through those. You're responsible for following the class procedure, right, and all these policies. Okay, so that's pretty much the Blackboard page. And you know by now, of course, that these lectures are going to be posted under assignments, right? These video lectures. Okay, so let me close this out. And we're going to head right into my very first lecture. Okay, so these are my PowerPoint slides that have been converted to PDF. And these PDFs are all posted on Blackboard under the same course documents folder. All right, so chapter 1, right, is our introductory chapter, and we are going to jump right into it, okay? So mechanics of materials is really a continuation of statics, all right? So statics is a prerequisite for this class, so I'm assuming that everybody's taken it, and you should have done pretty well in it, okay? And the reason I say that is statics forms the basis for everything that we do in mechanics of materials. Every single problem that you're going to solve in mechanics of materials is going to be first and foremost a statics problem. So you're going to be doing a lot of equilibrium, and there are going to be things like finding centroids, finding moments of inertia, and things like that. Okay, so you have to really be an expert in your statics before you can take mechanics of materials and expect to do well. All right. So if you've forgotten or if you think you're going to have some trouble with the statics, then make sure you go back and review those important topics. Okay. Let me briefly just list those topics for you then. Right. Everything is going to be in 2D, so that's the good thing. All right. You don't have to concern yourselves with 3D equilibrium, 3D moments of inertia, and things like that. Okay, so make sure you're caught up on 2D equilibrium problems, 2D centroids, and 2D moments of inertia. Those are the 3 absolutely critical things that you need for mechanics of materials. All right, so when you take a look at the mechanics of materials textbook, right? They go through some terms that are probably going to be fairly new to you, right? So don't worry too much about that. We're going to define all these terms as they come up. And let's start off by basically taking a look at a statics problem, right? So this is the example that shows up in your mechanics of materials book. And if you take a look at this structure here, you should be able to tell exactly what kind of structure this is, right? A lot of people want to take a look at this and say that it's a truss, and that would not be correct, okay? Let me give you a second to think about why this is not a truss. All right, so it is not a truss, right, if you go back to statics, because a truss, if you remember, starts off with a 3-member triangular shaped structure as a starting point. Okay, so this structure actually has just 2 members. If we were to connect A and C by a 3rd member, then this would be a truss. Okay, so thinking back to statics again, anything that's not a truss, right, would probably be a frame. So that's what this would be. Okay, so this is a frame. If this were given to you as a statics problem, what kinds of things would you be asked to find? All right, think about that for a second. Okay, so in statics, right, you're going to take a look at this and say, okay, this is one of those frames that's going to basically flop around if you remove it from its supports, right? This is not a rigid frame. So what that means is it is supported by two pin joints, right, at A and at C. So you think back and you're going to say, okay, a pin joint has two reactions, right? There's a vertical and a horizontal force reaction. So right off the bat, those are going to be four things that you're going to solve for in this problem, right? You're going to solve for four forces there, and then you're going to continue taking a look at this, and you're going to say, okay, I've got members AB and BC that are long and straight, right? There are no forces being applied anywhere in the middle of these members. So that means that these members are acting just like members of a truss, meaning that they're in either tension or compression. So the next two things that you would be asked to find if this were a statics problem is the tensile or the compressive force in the two members. Okay, and that would be pretty much it if this were a statics problem. Now, I'm not going to go ahead and solve the statics part of this problem for you, right? You should be able to do that yourself. If not, go back and review it, right? It will serve as a good exercise, just as a brief review. Okay, so, you would probably go ahead and dismember this structure, right? Apply equilibrium to each of the members, and so on and so forth. Okay. So we've got that. Okay. And if you go through that process, okay, this is what you find. You find that member AB is in compression and it's got an internal force of 40 kilonewtons, right? Member BC is in tension with an internal force of 50 kilonewtons, okay? And after you've done that, of course, you could go ahead and solve for the reactions at A and C as well. Okay? So that's statics. And as I mentioned earlier, mechanics of materials is going to build on this. Okay? So in what ways do we build on this problem? Well, here's how I'm going to explain it. Okay? Statics is what you could look at as an analytical type course, right? All the problems in statics are purely analysis problems, meaning you are given everything that you possibly need to know as far as dimensions of your structures, right? You're told how long the members are and things like that. And then what you're being asked to find are usually forces, right? They're going to be forces at your supports or internal forces in particular members. If you think about that, right, that's not going to allow you to design the structures themselves. Okay, so in statics, you look at structures that have already been designed, and then there are going to be some external forces applied to these structures, and you end up trying to find reactions and internal forces. Mechanics of materials is going to take this a step further, right? It's going to start considering the material that these structures are made out of. Okay, and that's going to be very important in a real life situation, because if you take a look at this structure, right, we have no idea whether your pin joints, right, at A and C, and then even the pin joint at B, and then the members A, B, and BC, we have no idea whether they're able to withstand that 30 kilonewton force that's applied, right? And the reason we can't really make that determination is because we have no idea. And we actually don't care in statics, right, what material these pieces are made out of, okay? It's pretty obvious that depending on what material these members are made out of, the structure is either going to be stronger or weaker, right? It might be able to withstand much more than 30 kilonewtons, let's say, right, if we were to make this out of something that's very strong, like steel. Or if we make it out of a pretty flimsy plastic, let's say, right, it actually may not be able to even withstand the 30 kilonewtons. We don't care about that in statics, right, because statics basically gives you the tools to analyze these structures It doesn't give you the tools to design these structures, right? The design problem has to take into consideration materials. So that's where mechanics of materials is going to come in. All right, so how are we going to do that? How do we bring material into the design of these structures? Okay, in order to do that, okay, we cannot rely on forces, on just looking at forces. Okay, we need something else. And what we're going to be using is referred to as a stress. Okay, so by pure definition, right, this is just a definition that we've come up with. Stress, okay, in particular what we call a normal stress, okay, and I'll get into that in a minute, is defined as your internal force, we're going to call that P, capital P, right, divided by the cross-sectional area. So what's the cross-sectional area? Well, you have these long, thin members, right? The cross-sectional area is basically if you make a cut anywhere on this member, right, what that area would be. So in this example that's shown here, you can see that it's a circular member, right? It's a member with a circular cross-section, in which case the area would simply be pi times the radius of that circle squared, right? So that's a very simple definition, and that should kind of set off a light bulb, if you will, right? Because you've seen something like this before. Anytime you take a force and divide it by an area, right, what you're really doing, right, based on pretty much what everybody knows, is you're calculating a pressure, okay? So we are now going to kind of use this pressure value instead of a force, okay? And that is going to go a long way towards helping us bring material into the design problem, okay? And I'll explain all of that in just a minute here. Okay, so why stress, right? So here's my explanation. All right, so stress is more or less a pressure, right? So let's start off with this thought exercise here. All right, I'm going to have two balloons, okay, of the exact same size. Let me bring up my pen here. I've got two balloons of the exact same size and the exact same shape. Okay, so there's one, here's another, right? So these are the exact same size and shape, but this balloon is made out of one type of rubber. I'm going to call this rubber 1, right? And it's got a certain thickness, it's got a certain strength, if you will, right? And then this is made out of rubber 2, right? A completely different material. What I want to do is I want to blow up these two balloons until they both burst, right? If these are two completely different materials, right? They have different thicknesses, different strengths. Are they going to burst at the same pressure? Right? It should be pretty obvious that they will not. Okay. Now, I'm going to take that rubber 1, right, and make a different balloon out of it. I now make something, let's say I'm going to make a completely different size and shape of a balloon, right? But it's made out of the exact same material, rubber 1. I have the same sheet of rubber that I used to make the first balloon, and I just use it to make the second balloon. And now I blow this up until it bursts, okay? Are these two balloons going to burst at the same pressure? The answer is yes, okay? Why? The explanation is dependent, it's kind of based on the idea that they're basically built from the exact same material, okay? And what that means is this material, this rubber 1, right, has some bursting strength, okay? There's a certain pressure that will cause this rubber to burst, to break, okay? And once I know that, Okay, it doesn't matter what shape or what size I make my balloon out of. I know it will break at the exact same pressure. Okay? Let me get rid of the rubber 2 here. Okay, there's my eraser. Let me erase it. So you can see that if we use pressure as our measure of what's going to cause these two balloons to break, then all that the breaking pressure is going to rely on, is going to depend on, is the material that these balloons are made out of, right? On the other hand, what if we were to use a force, right? The breaking force to burst these two balloons. So what that would mean, right, is each balloon, of course, okay, has forces pushing all throughout the inside, all pushing all throughout the inside surface, right? So if you were to integrate those forces over the whole inside surface, or basically sum up all those forces, you're gonna get some total force, right? F equals, that's, you know, it's some integral of dF, if you will, right? If I add up the forces, if I add up the total bursting force for this top balloon and compare it to the total bursting force for that second balloon, would they be the same? Okay. The answer here now is no, right? They're completely different because they're different size and different shape, right? They're the same material, but they're different size and shape. So which of these quantities, right, allows me to make a comparison based on the material? It's going to be when you use pressure instead of force. Okay, when you use something like pressure, the very fact that you're dividing your force by the area, right, what that means is you're removing the effect of area out of that quantity. Okay, so when you use pressure to make the comparison, then you don't even have to worry about size and shape. Okay, so pressure basically now is a quantity that becomes shape and size independent. Okay, and that's exactly what we want when we start designing structures. Okay, so let me kind of relate this now to mechanics of materials and structures, right? That rather than balloons. So I'm going to have simple columns. Okay, so I've got this simple column. Let's say this is made out of steel, right? Then I've got another simple column, exact same size and shape, right? That's maybe made up of aluminum. Okay? And then I'm going to have a third column that's much smaller and it's got a completely different shape, right? And I will make this out of steel. Okay? What I'm going to do is I'm going to push with a force on each of these three columns until each column breaks. Okay, so what we call that is sort of the breaking force, if you will, right? So I'm going to call that F break. So I'm going to have some value for this first column, a value for that second column, a value for the third column. Are they going to be the same? Obviously not, right? We know steel is much stronger than aluminum. So this first column, right, is the force required to break this first column is going to be much greater than the force that's required to break the second column and the third column, all right? How about the force that's required to break the two steel columns? Why is the force that's required to break the first steel column much greater than the force that's required to break this second steel column? Well, it's obvious, right? The first one is much larger than the second one. So something that's larger and made of the same material is obviously going to be stronger, okay? So this is a bad comparison, right? If I try to use force to kind of compare these three things, values are going to be all over the place, right? I really can't make much of a comparison. In fact, right, can I say that the steel that's used in the first column is stronger than the steel that's used in the third column? No, right? They're the exact same material. Okay, so what if I use the pressure now? What if I were to take this braking force, right, that's for each of these three columns, and then divide it by the cross-sectional area of each of these three columns? What I end up with, right, is now the pressure or the stress. Remember, we came up with this quantity of stress now that's very similar to a pressure, right? So stress, okay, now is each of these forces divided by the individual areas, right? I'm going to call these area 1, area 2, and area 3. If I take the three stress values now and compare them, right, how do you think they're going to compare? The first stress value, right, for this large steel column is going to be much larger than the stress value for that aluminum column, right? Because the force in the first column was much larger than the force in the second column, but their areas were the same, okay? How about if I were to compare stress in that first steel column to the stress in that second steel column? Here's the great thing, right, if you were to make that comparison. These will be exactly the same, these two values, okay? And the reason for that is that they're the same material, okay? Once I kind of take size and shape out of the equation by dividing by the area, then what I'm left with is just the effect of the material itself. And we know that steel itself has a certain strength, right? Steel is steel, right? As long as I heat treat it the same way and produce it the same way, I know steel is steel. It's got certain properties. It's got a certain melting point, right? It's got a certain conductivity. It's got a certain density. Well, just like all those other values, right? Steel has a certain strength to it, okay? So the way I can make use of that strength, right, is to use this idea of a stress rather than using force. Okay? So there's our definition for stress. Okay? It's just the force, that's the internal force now. Okay? That's very important to keep in mind. In mechanics of materials, anytime we talk about forces and members, right, or stresses, we are always referring to internal forces. Okay, because external forces could be anything, right? External forces could be a force that's applied somewhere, or it could be a reaction force at a support, right? Those don't really have anything to do with the strength of the material itself. Okay, so remember, keep that in mind, right? Anytime we talk about stress in mechanics of materials, we are referring to the internal force divided by the cross-sectional area. All right, so going back to our definition of stress, right? This is what we call a normal stress. And normal stress, right, if you take a look at this word normal itself, right, another word that we can use is perpendicular, right? So what that means is normal stresses are defined anytime you have a force that's applied perpendicular to a cross-section, right? So what kind of situations are we looking at here? Well, anytime you have a force that's perpendicular to a cross-section, that force is going to be tensile or compressive, okay? So normal stresses are always going to be tensile or compressive. Okay, so when a member is in tension, then it's got a normal stress. When a member, it's got a tensile normal stress. When a member is in compression, it's got a compressive normal stress. Okay, and in mechanics of materials, we're going to use a sign convention. Okay, positive is always tension, and negative is always compression. Okay, this just makes things a little easier. Right now, you could go ahead and use positive and negative signs rather than having to always specify whether something is in tension or compression, like you had to in trusses from statics. Okay. The next thing that is very important here, okay, is this symbol that we use for stress. This is Greek letter lowercase sigma, okay? So very important. Okay, so do you have to memorize the Greek alphabet for mechanics and materials? No, right? It's not really a necessity, but you do have to memorize the symbols that we will be using, okay? And there are going to be quite a few of these symbols, and a lot of them are going to be Greek letters, right? There will be some regular alphabetical letters as well, right? But you just have to get used to this, okay? Here's the great thing about these symbols is they're pretty much universal, okay? In mechanics and materials, we have almost a standardized notation. So these Greek letters are used throughout the world by engineers everywhere, okay? It's not like physics, right? Where your symbols are gonna differ even from just textbook to textbook, okay? So it's nice, right? You only need to memorize this once. And once you learn this, right, if you go and work for some company after you graduate, you're going to be using these exact same symbols in your job. Okay, so there is our first formal definition. Okay, sigma is equal to P over A. That's what it's going to be simplified as. Okay, so sigma equals P over A, right? Where sigma, again, is the normal stress. P is the tensile or the compressive force, and A is the cross-sectional area. All right, so hopefully I've convinced you that making use of this normal stress is better from a design perspective than simply using the force, right? And this is going to be very important for us, right? Because we're going to use this now throughout the course. All right, let me erase these from my board. All right, so what is the difference between normal stress and pressure, right? Because they pretty much have the exact same definition. So let me explain that. What type of a quantity is pressure? Is it a scalar or a vector quantity, right? Hopefully everybody said immediately that pressure is a scalar, right? And you would be correct. Normal stress is not a scalar quantity, okay? So that's the big difference, okay? Kind of like the difference between speed and velocity, right? Speed is simply the magnitude of your velocity. Right? Velocity has a direction, speed does not. It's the same thing when it comes to normal stress, okay? So pressure has no direction to it, right? When we talked about pressure on the inside of that balloon, all we know is that it's pushing perpendicular to the wall of the balloon in all directions, right? There was no particular direction. Well, normal stress does have a direction. Okay, so look at stress as sort of the vector equivalent of a pressure. All right, so let's continue on. Bear with me here. Okay, so I already talked about how stress, right, allows us now to make direct comparisons. It allows us to bring material into the picture. Right? And what we're going to do now is we're going to go back to this problem that we talked about earlier, right? So we had this frame problem, and we said if this were a statics problem, you would have found the reaction forces at joints A and C, and you would have found that AB, right, is under compression with 40 kilonewtons, BC is in tension with 50 kilonewtons. And now that you know what the sign convention is that we use in mechanics and materials, right, you could even go ahead and say that the force in AB is negative 40 kilonewtons, right? And that the force in BC is positive 50 kilonewtons. Okay? So how do we apply this idea of stress to those two members? Well, it's very easy, right? If you take a look at this original problem here, you were told that member BC had a round cross-section with a diameter of 20 millimeters, whereas member AB was a rectangular cross-section that was 30 by 50 millimeters, okay? So knowing those dimensions, you could obviously calculate the cross-sectional areas, and then once you know the internal forces in those members, you can go ahead and calculate stresses in those members, okay? So that's exactly what we're gonna do, okay? Let me go back to that in a second. So sigma is F over A, right? You can calculate the stress in BC, calculate the stress in AB. Now, units of stress, right? So because stress is very similar to pressure, it's going to have the same units as pressure, right? So in the SI system, your units of stress are going to be in newtons per meter squared, right? And that's given its own unit, which we refer to as the Pascal, abbreviated capital P, lowercase a. How large is a Pascal? Right? Kind of try and get a feel for how large a Pascal is. So how large is a Newton? Right? A Newton is actually pretty small, right? It's fairly tiny. And a meter is, it's fairly large, right? So a Pascal is pretty small. So if you start thinking about what kinds of problems we're going to be looking at, right? We're looking at structures, and by structures, we're talking about things that that support usually pretty large loads, right? We're looking at parts of machines. We're definitely looking at parts of bridges and parts of buildings and things like that, right? So first off, the forces are going to be huge, right? And what that means is the pressures are going to be huge. We're talking about millions of pascals, right, in a lot of cases. So the nice thing about the SI system is you can go ahead and make use of those prefixes, right? So a lot of times engineers don't use pascals, right? They instead use kilopascals at least, right? That's 1,000 pascals or 10 to the third. Then we use megapascals, right? That's 10 to the 6 or 1,000,000 pascals. And then in some cases, we actually use gigapascals, right? That's GPA, 10 to the 9th pascals, or 1 billion, right, pascals. And, usually the ranges of stresses on structures that we're going to look at, right? And by that, I'm usually referring to things that are more civil engineering related, right? So members of bridges, of buildings, things like that. Those are usually going to be in the order of tens to hundreds of megapascals, okay? So the megapascal is very commonly used, okay? Does that mean that you are incorrect if you express your answer in terms of pascals, right? Like 400 times 10 to the 6 pascals? No, right? That certainly mathematically is not incorrect, right? However, you probably want to get used to this idea of using these prefixes because that's what most engineers out in the field use. All right, so that's the SI system. Okay, and just one more quick thing with that. A lot of people tend to mix up megapascals and gigapascals. And think of the repercussions if you make a mistake, right, between megapascals and gigapascals. You're talking about an order of magnitude of 1,000 times, right? That's the difference between 10 to the 6th and 10 to the 9th. So your answers, if you make that mistake, are going to be off by a factor of 1,000. Right? That's certainly a large mistake to be making. So get used to the difference between mega and giga, right? 10 to the 9th for giga, 10 to the 6th for mega. All right, how about the US system, right? And I'm sure you learned this in statics, or you saw this talked about quite a bit in statics, right? Here in the United States, okay, you as the engineer have to be comfortable using both the SI system and the US system, right? The rest of the world pretty much uses SI. The US and Liberia, I believe, right, is the only other country. We're the two countries that use our US system. So Unfortunately, what that means is if you study engineering in the US, right, you have to be comfortable with both, because once you start dealing with engineers in other countries, they're going to be using only SI. So you have to be comfortable with that. But then if you work with engineers in the US, they might be using the US system. Okay, so you have to be comfortable with both. And the problems that you're going to be solving in this course are going to be split pretty evenly between SI and the US. Okay, just so you get practice using both systems. All right, so when it comes to stress in the US system, right, the units are going to be in pounds per square inch, right, abbreviated PSI. And how large is a PSI? Well, it's larger than a Pascal, right, but it's also still pretty small. Okay, so what we do is, you might remember this unit of that's referred to as a kip, right? A kip is 1,000 pounds. And where that comes from is we borrowed that kilo prefix from the SI system, right? And we create what's called a kilopound, right? Or 1,000 pounds. And 1,000 pounds per square inch is a kip per square inch, and we abbreviate that KSI. Okay, so that is commonly used when we deal with the US system. Okay, so there you have it, right? Those are the units that we're going to be using, okay, when it comes to stresses. Okay, so with that out of the way, right now we could take a look at how you're going to calculate the stresses in that frame problem that we talked about earlier. Okay, so member BC, if you remember, was the round cross-section, diameter of 20 millimeters, right, had a tensile force of 50 kilonewtons. So the stress in member BC, right, is 50 kilonewtons, which is 50 times 10 to the third newtons, divided by area, which is pi times radius squared, okay? And if you work that out, that's 159 times 10 to the 6 pascals, or 159 megapascals, okay? So we'll go back to this in just a second. Right? And what you can do is you could go ahead and calculate the stress in the other member. Give me a second here, right? I'll come back to all of this. And member BC, right? We have, let me see, where was it? I'm sorry, member AB, right? Member AB was the member that was in compression, right? So the area in that member was rectangular, right? So it's 30 millimeters times 50 millimeters, gives you an area of 1.5, 10 to the negative 3 meters squared. The force, remember, it's compressive, right? So it's a negative 40 times 10 to the third newtons, giving you a stress in member AB of negative 26.7 megapascals. Okay. Notice how I calculated these values here, right? Your diameter in BC, your diameters and your lengths were given in terms of millimeters, right? And your forces were given in terms of kilonewtons. However, when you go ahead and calculate your stresses, what you notice here is that everything is converted to base units, okay? And that's, you know, probably this is probably what you'll want to do until you get very comfortable with it, right? So if you were to leave your diameter in terms of millimeters, right, and your force in terms of kilonewtons, what do you end up with for your stress is going to be something that's going to be in kilonewtons per millimeter squared, right? How many pascals is that? Well, I have no idea, right? And I've been doing this for several years, okay? So I have no idea how many pascals that actually is, right? So you could certainly go ahead and try and work it out, but it's much easier, right from the start to convert all your dimensions to meters, right? So 20 millimeters is 0.02 meters, right? So I'm going to use that as my diameter, right? And then 50 kilonewtons, right, is 50 times 10 to the third newtons. I'm going to use that as my force, right? And if you do that, that will give you a result directly in newtons per meter squared or in pascals, okay? So that's the best thing to do when it comes to calculating your stresses. All right. So let me go ahead and erase all of this. I know there's a button that will erase everything in one shot, but I haven't figured that out yet, so bear with me. All right, so now we can calculate the stresses in A, B, and BC, right? But what exactly does that do for us? Any ideas? Right, I'll give you a few seconds to think about that. I mean, you know, rather than saying that AB or that BC has a tensile force of 50 kilonewtons, now what we're really saying is BC has a stress of 159 megapascals, right? What's the difference, right? Both numbers really don't mean too much to you at this point, I would imagine. Well, here is the great thing, right, with using stress. I had said earlier that the strength of a particular material is a property of that material, okay? And that is absolutely true, okay? Now, how do we bring material into this problem? Okay, and let me try and explain here. Okay, so give me a second. Unfortunately, I don't have a scan of the appendix of the textbook, right? But those of you that have a textbook handy, okay, what I want you to do is I want you to go ahead and flip to the back of the book, right? I believe it's probably Appendix A, okay? Appendix A, which basically is a table of a bunch of different materials that are commonly used in engineering, okay? If you look through that list, it's mostly metals, but you also see a few different woods, right? And some different plastics on there. And you'll see concrete as well, right? But it's all these materials and then their material properties. So you'll see things like density, right? You'll see things like probably, I'm not sure if melting point is on there, but definitely conductivity, right? Coefficient of thermal expansion, right? But another quantity that you're going to see on there is what's referred to as an ultimate strength. Okay? Give me a second here. So since I don't have the textbook available with me, okay, what I'm going to do is try to find one on the internet. Okay, so I'm going to Google table of material properties. Okay, and see if I could find one that's online. Okay, so the very first link that Google gives me, right? Okay, brings this up. Unfortunately, this doesn't have it in tabular form, right? It's got just a bunch of links, but let's see. So steels are very common, right? I'm going to click on properties of steels. All right, so look what comes up, okay? You've got a bunch of different steel alloys, right? They're all processed differently, hot rolled, coat drawn, and so on and so forth. And then you have a list of values here, okay? And if you take a look at, let's see, the first four columns, there's yield strength, right? Tensile strength, yield strength in MPAs, tensile strength in MPAs, right? So these are values that are given in both US units and SI units, okay? And let me explain these. So yield strength, okay, is something that we're going to get into a little later on. But tensile strength, okay, that tensile strength value is extremely, extremely important. Okay, what these values are are the stress, right, at which that particular steel is going to break at. All right. So if you take a look at that hot rolled steel in the first row, all right, you see that its tensile strength is 47 KSI or 324 megapascals, right? And 324 megapascals. Let's write that down, right? 324 MPa. Okay? And that value is what we refer to as a sigma subscript ULT for ultimate. Okay? It's what we call an ultimate strength, now on that table that we just pulled up, that was referred to as tensile strength, right? Because they tested it in tension rather than in compression. Okay, but usually for a lot of different materials, the tensile values and the compressive values are almost the same. All right, so in a lot of textbooks, that's actually just referred to as an ultimate strength, okay, or an ultimate stress. Okay, and ultimate simply means that it's the stress at which it breaks. How do you think they came up with that value? Well, it's pretty simple, okay? We'll get more into this next time in the next lecture, but you can imagine that all they do, right, the engineers who came up with this, is they just took steel, right? They took a whole bunch of hot rolled steel samples, and then they formed probably a few different formed a few different members out of it. Okay? All different sizes and shapes. Okay? And then all I'm going to do is I'm going to somehow pull on each one of these until it breaks. All right? I probably grip one end and then just keep pulling on the other end, right, until it breaks. And then I note down the force at which it breaks. F break, let's call it. Right? And then what I do is I take every single one of those braking forces, right? Let me ask you this, right? If I take these 4 braking forces, are they going to be the same? The answer is no, right? So even though these are all hot rolled steel or cold rolled steel, as whatever the case is, right? Even though these are all the same material, they're different size and shape. So they're going to break at different forces, right? But then what I do is I divide each by the area. And what have I come up with? I've come up with a bunch of different ultimate stresses. Okay. Are those 4 ultimate stresses going to be the same based on everything we've talked about up to this point? The answer is yes, right? These are all made out of the same material. Once I divide by the area, I'm taking size and shape out of the equation. Okay, so they are all going to break at the same stress because they're all the same material. And this has been proven over and over, right? Engineers have just proven this through a lot of experiments over the years. Okay, so that's where those values in that table come from. Okay, people just perform all these tests and they find that steel, right, a particular alloy of steel will always break at that exact same stress value. Okay, every time. All right, so going back to our member BC, right? We know that it's got a stress of 159 megapascals, right? And if you were the engineer now, and your task in this particular case was to pick a material, right, to make this structure out of, right? What you would do is you would go through a table of materials, right? Go through something similar to that table that we just pulled up, and then you would start looking at all the different ultimate stress values that are listed. Okay, And certain materials are going to have ultimate stress values that are probably going to be less than 159 megapascals. Okay? Are you going to choose those materials? No, right? Because if you were to choose a material with a ultimate stress that's less than 159 megapascals, and you know that this member BC has to support 159 megapascals, then the material you choose is going to break, okay? And that's obviously what you do not want, okay? So how would you choose your material then? Well, you go through that list, right, and you pick something with an ultimate stress that's greater than 159 megapascals. So will our steel work, right, with the ultimate stress of 324 megapascals? Yes, right, that would be definitely something that would work, all right? Now, your question for me then might be, well, there are going to be a lot of materials with an ultimate stress greater than 159 megapascals, right? How do I know which one to choose? Well, there's a lot more to design than simply looking at these numbers, right? Another important part of design is cost, right? And that's especially true these days, right? Economics is a huge issue within engineering, right? You as the engineer, you don't just design something that's going to work, that's going to withstand any abuse that people put on it. You also want to design something that's affordable, right? Or design something that's as cheap as you can make it, okay? So that's going to be another consideration that you would make, right? So you might have a whole list to choose from, right? You might come up with a list of materials that include steel and titanium, right? Maybe magnesium, right? And then from your list, right, you will probably end up choosing something that's probably the most readily available, that's the cheapest, right? And sometimes the lightest, okay? And so on, all right? So that's how using stress is going to help you in this situation, right? If you were just using that force value, right? If you were just using that 50 kilonewton force value, how are you going to be able to decide what material to choose? You would have no idea, right? Because you might say, well, I know steel could probably withstand 50 kilonewtons, right? But will a steel with a diameter of 20 millimeters be able to withstand 50 kilonewtons? You really have no idea, right? I mean, what's the size limit, right, if you were to use steel, right? Another way of putting this is, well, I know that I could use something that's really weak, right? Maybe I choose like some kind of a very soft plastic, right? And I'm going to say, well, I know that this plastic could withstand 50 kilonewtons, right? But there's no way I can make its diameter 20 millimeters. That would be just way too small, right? If I were to choose a very weak plastic, I might have to make it 50 millimeters in diameter, right? And depending on the situation, that might not be allowable, right? Maybe your customer already comes to you with a bunch of requirements, and one of the requirements is BC has to have a diameter of 20 millimeters, okay? So these are all different design issues that really come into the picture, right? And we'll start to get into more and more of this as the course goes on, okay? All right, so hopefully that illustrated for you why the use of stress is now very important, right? Especially when you start considering the materials that you're going to make your structures out of. Right? And the same thing is going to be true for member AB, right? This was member BC, right? 50 kilonewtons of tension. We of course have member AB as well, right? That was under compression, and you would do the same thing, right? You would take a look at its stress, and if you were to choose a material to make AB out of, you'd want to choose something with an ultimate stress value that's greater than whatever the stress was, okay? Which brings me to this next slide here, right? Let me just quickly go over this. Yeah. Mechanics of materials is what I refer to as a design class, right? I said earlier at the beginning of this lecture that statics is an analysis course, right? And let me kind of reiterate what that means, right? In statics, every single problem that you're given, you were told exactly what the dimensions of each member was, right? You were told what all the applied forces were, and then you were simply asked to find internal forces or forces that supports, okay? In mechanics of materials, we also have some analysis problems, right? This problem that we had earlier could very easily be an analysis problem, right? And the analysis problem would simply be, given this structure, right? Given that BC has a diameter of 20 millimeters, what is the stress in BC? That could be the only thing that I ask, right? And in that case, that would be an analysis problem, right? How do I make it into a design problem? The design problem now is going to be very similar to what we discussed earlier, right? Given all of this, right, what material should BC be made out of, right? Or give me a possible material that BC could be made out of. That's one thing, right? Another thing might be, I don't give you that 20 millimeters, right? I might simply say, I want BC to be made out of aluminum, okay? I know BC, and you have to tell me what diameter to make BC, okay? That now becomes a true design problem, right? Because now you actually have to design the member itself, right? And by designing a member, of course, we're talking about things like dimensions, right? How long to make it, what diameter to make it, right? What shape to make it, so on and so forth, okay? So that's one thing. Another thing would be, I might give you all the dimensions of a structure, and then I might ask you, right, how much force I could actually apply to that structure, okay? So that would be a case where you already have a product that's designed that you want to sell to someone, right? And before you sell it to someone, you have to tell them basically how much force they could apply to this product that you're trying to sell them, okay? So let me try and illustrate this a little better for you, okay? So let me use a very simple case again. So we're going to be looking at a steel column, right? This is probably the simplest case. So I've got this steel column that I'm designing, right? Here's the analysis problem. The analysis side of this would say, okay, this steel column is going to have a force of 50 kilonewtons applied to it, right? It's going to have a diameter of 0.5 meters. Okay? Find the stress. Find the stress in this column. That would be an analysis problem. That's the simplest type of problem that you can encounter, right? And how would you solve this? You say sigma is equal to P over A, right? You know that this is compressive, right? So this is going to be a negative 50 times 10 to the third newtons divided by pi times radius is 0.25 meters squared, okay? So you work that out and you get a stress value, right? That would be an analysis problem. What is one variation of the design problem? It would be simply adding to what we just did, right? And now saying find stress and choose a material to make this out of, right? Choose material. And how would you do that, right? you would do exactly what we discussed earlier, right? After you calculated that stress, you would go to a table of material properties, and you would choose a material with an ultimate stress value that's greater than that stress value that you calculated. Okay, so that would be the first design problem that you might encounter. What other design problems can we create out of this, something like this? Right, so here's one. I'm going to have this steel column. I have a steel column. All right, so your customer comes to you and says, I need you to design for me a steel column that has to support 50 kilonewtons, right? I need you to tell me how large to make this column. So basically your task now is to find the diameter, right? So how would you solve this problem now? Well, steel has a certain strength to it, right? Let's say we go ahead and use that previous value that we looked at, 324 megapascals, I believe it was, right? So you know that stress is still sigma is P over A, right? But now you know that the largest stress that this column could withstand is the breaking stress, right? If you go any larger than that, then obviously this column is going to break, right? So you go right up to that limit, 324, right? Times 10 to the 6 pascals is equal to, I know I'm going to apply a force of 50 kilonewtons, 50 times 10 to the 3rd newtons, right? Divide by area. Area is pi times radius, which is your diameter over 2 squared. Notice that your diameter is the only unknown in this equation. Right? So all you need to do is solve for D in this equation. And what is that going to give you? That tells you basically that you do not want to go any smaller than that diameter. Right? Think about what happens here. If I have a value of D that gives me exactly 324 times 10 to the 6 pascals, right? That's the breaking point. If I make D any less than that, right, then this denominator is going to get smaller, right? And then when I divide 50 times 10 to the 3rd by a smaller denominator, what happens? I'm going to get a result that's greater than 324 times 10 to the 6 pascals, right? So what that means is I'm going to exceed the breaking strength of this material. So when you solve a problem in this way, right, the diameter that you solve is the absolute smallest that you're able to get away with, right? So when a customer comes to you and tells you, I need this steel column to withstand 50 kilonewtons, what you go back to them with is, this is the absolute smallest that you should make your column, okay? If you make it any smaller than this, your column will break, right? It will fail. Now, can you make it larger than this? Of course, right? If you were to make D now larger, then what you're doing is you're dividing your 50 times 10 to the 3rd newtons by something that's larger and larger. What that means is your stress is going to be less than 324 times 10 to the 6 pascals, right? So you're actually going to be lower than the breaking limit of steel, right? Which of course is fine, all right? However, of course, right, the larger you make D, the more material you're going to use and the more cost you're going to incur, right? So in a problem like this, you're going to be solving for the smallest amount that you could get away with, okay? So that would be another design variation or another variation of the design problem, all right? What is yet another variation? Okay, so another variation on this is going to be, the customer comes to you and they say, well, no, actually now you might not have a customer that comes to you, right? Now you're just designing something that you're going to sell, right? So you've designed this column that you're going to make out of steel, right? And you know that this column is going to have a diameter of 0.5 meters, right? And when you go ahead and sell this, you have to tell your customer, right? This is the largest force you could put on this column, okay? If you put any more than this force on this column, then this column will break, okay? And I will not be responsible, right? Because when you sell something, you've got to give specifications, right? And you tell your customer, do not exceed this value, right? If you exceed this value, I am warning you ahead of time that this will break, right? And you will be responsible for whatever loss you have because you were already warned what the limit was, okay? So how do you solve this problem now? Well, it's all the same equation, right? Sigma is P over A, right? So again, I hope this is becoming clearer and clearer to everyone, right? That when you make use of this stress value, okay, you could bring all these design problems into the picture, right? You could start accounting for different materials, right? All right, so how do you solve this now? Well, again, you look up the strength for steel, right? You say, well, I know steel is going to break at 324 megapascals. So 324 times 10 to the 6 pascals, right? And I just need to find out what force brings me exactly to that breaking limit, brings me right to that breaking point, right? And then I know my area, right? It's pi times the radius, which is 0.25 meters squared. And you notice now that your only unknown is P, right? You solve for P, and what does that mean? That means if you apply a force equal to whatever this value of P is, then you go right up to the breaking point. And once you know that, then this is what you tell your customer, right? You will say, do not apply any more than this value P, right? If you exceed this value P, then you're exceeding the strength of the material and the material will break, okay? If you apply less, then of course it's going to be fine, all right? So that is pretty much the last variation of the design problem, okay? So these are all the different types of problems now that you're going to encounter in mechanics and materials, okay? You don't simply have these analysis problems anymore, right? Analysis problems are still going to be asked of you, but more often than not, you're going to start encountering these different design problems. All right, so just wanted to get you used to that. Let's go back to the slides here. All right, so we've got calculation of stress. Okay. This whole idea of a normal stress. Let me skip through all of that. Okay. So next is the idea of a shearing stress. Okay. And a shearing stress now is completely different from a normal stress. Right? A normal stress happens whenever you have tensile or compressive forces, right? But a shearing stress, okay, is going to be very different. And let me kind of explain what's going to happen here with the shearing stress. Right? So this figure is probably not the best way of introducing shearing stress. Okay, so let me draw something for you. If you have two blocks, okay, two blocks that are bolted together. So I drill a hole through both these blocks, right? And I put a screw through. Doesn't even have to be a screw, it could be a rod, right? But I put a screw through both these boards. And then I pull at the ends of these two boards in opposite directions, right? What happens to that screw? Well, you can see that right at the junction here, right at the junction where these two boards meet, right? At that junction, this screw is actually being torn apart, right? This bottom half is being pulled towards the right, and this top half is being pulled towards the left, right? So right at that junction, right, that's what we call a shearing plane, because that's the plane at which this screw is being basically split in two, okay? And that's also a kind of stress, okay? Except that it's a shearing, right? This term shearing or shear, right, means that basically you're trying to rip something apart, if you will, right? You know, people refer sometimes to scissors as a pair of shears, right? Because what you do is you use it to tear a piece of paper apart, right? Or something like that, okay? So a shearing stress, obviously, if you look at this, is very different from a normal stress. A normal stress on the screw is if you were to pull the screw, right, along its vertical axis, right? That would be putting a normal stress on the screw. But now, when you pull sideways on the screw, right, now you have shearing. So a shearing stress, okay, is definitely very different from a normal stress, okay? And how we're going to define it, okay, is very similar. We're going to say, again, that it's a force per unit area, P over A, right? But now the force that you're applying is not perpendicular to the cross-section. It's parallel to the cross-section, okay? So here is a new Greek symbol for you. Greek letter tau, okay? Tau is a shear stress. Now, some textbooks call this a shear stress, and some call it a shearing stress, right? So it doesn't matter what you use. They're pretty much the same thing, okay? So shear stress. Is it also a pressure? Sure, right? Except now it's not a pressure that's basically pushing against something. It's a pressure that's basically rubbing against something, if you will, right? So if you were to take the palm of your hand, push it down on the table, and now slide your hand across the table, are you applying a pressure to the surface of that table and applying a pressure to your hand? Yes, right? Except now the pressure is in what direction? It's not perpendicular to that table, right? It's in the plane of that table. When you rub your hand across the surface of that table, the pressure you're applying is along the surface of the table, right? That's a shear stress. It's still a pressure, right? More or less, except it's not a perpendicular pressure anymore. It's now a rubbing pressure, if you will, right? For lack of a better term. All right, so the next thing here, okay, is the subscript. Why is there an AVE or average, right, subscript for the shear stress? So let me go ahead and explain that. Okay, let me go back to a normal stress, okay? In a normal stress, right, I've got this column. I might pull it in tension, right? When I apply a force to this column, right, and I take a look at the cross-section, how is that force distributed over the cross-section? Well, people have done experiments on this, right? And what they find is that obviously it all depends on how you apply this force at the end, right? If I apply a point force, I just kind of apply this force at a single point and I pull, then obviously right on the surface where I'm applying that force is only applied here. But people have found that very quickly, as you go further and further away from that surface where the force is applied, that force starts to spread itself out. Okay? And that means by the time you get a certain distance away, that force is evenly distributed over the cross-section. Okay? So even though when you do sigma is P over A, right, that's also an average, right? It's averaged over the whole cross-section, meaning you take this cross-section, and if you break it up into a bunch of little pieces and take a look at the force on each of those little pieces, and then average it all up together, that's the value you get. Even though you could do that, right, because that force is evenly distributed, the average is actually the same as the value anywhere on this surface. Okay, so using an average doesn't really mean anything. It's an absolute value. It's an exact value. Okay, when it comes to shear, okay, that is definitely not the case. Okay, and we'll get more into that in chapter 3 and chapter 6. I'm sorry, in chapter 6. Okay, is where we'll get into that. Right. So when it comes to shear stress, okay, you can't assume that the average is also the exact value that you have over the whole cross-section. Okay, what you're going to find later on is that in fact it actually varies from 0, okay, at some locations on that surface to some maximum value at other locations. Okay, so it's a huge difference. All right, so hence we use that subscript, okay, for tau average. And what that means is this is actually not a very meaningful value. Okay, if the actual value across the whole cross-section is going to range from 0 to some maximum, then what is the average really telling you? Well, you're averaging out a bunch of values from 0 to some maximum, right? And the average is somewhere in between. Doesn't really tell you very much, okay? It kind of gives you an idea, of course, right? But you wouldn't design a structure based on an average shear stress. Okay, so even though we talk about average shear stress in this chapter, in this first chapter, it's just to introduce the idea of a shear stress. Okay, we're going to get into much greater detail of shearing in later chapters. All right. So anyway, all right, let's move on. So this is the example that I had given you earlier, right, for shear, right? You have two boards, you put a bolt or a screw through those two bolts, you pull those two boards apart, right? You're going to get a shear stress right at the junction of that bolt, okay? This is what we call a single shear because there's one junction that's being pulled apart, right? The figure on the bottom here is what we refer to as a double shear, right? And this is a case where you're joining three boards together, right? So look, you join three boards together, right? You have the two that are kind of this tan color, and then you have the one that's more or less a gray color, right? So imagine now that I pull on that gray board towards the right, and then I pull on the two tan boards towards the left, okay? How many junctions do you have now? You obviously have two junctions, right? There's a junction here and a junction there on that screw, right? Here and here. And what that means is the force that you're applying is now shared between the two different areas, okay? So there's two ways of looking at this, right? If you were going to calculate the average shear stress on this screw, you could either take that force divided by 2, because there are two junctions, and then divided by the area of each junction, right? Or you could say that you're going to take that single force and divide it by twice the area because you have two junctions, okay? Either way is fine, right? They obviously give you the exact same result. All right, so that's shear stress, okay? And as I said, kind of get used to this idea of a shear stress, right? But in later chapters, you would never calculate shear stress by simply taking a force and dividing it by an area, right? Because it's not very meaningful. Okay, So now that we have all of this, right, actually there's one more type of stress that we're going to talk about very quickly. And again, this is not used very often, right? This is just to kind of get you used to this idea of a stress. This is what we call a bearing stress, okay? So a bearing stress is just another form of a normal stress, okay? And all it is, as that figure was showing, right? If you have a screw, a bolt, or whatever that sits in a hole, right? If you have a screw that sits in a hole, and that screw is being pushed or pulled against that hole, right? Let me see if I could explain this a little better here. So we had this member. We had a member, right? Whether it was A, B, or B, C, it doesn't matter, right? So you have this member, and let me redo it. So here is the support. Here's the pin joint, right? There's the wall. There's the pin joint. Here's the member, right? And this member was in tension, I believe. Right? So this member is in tension, so you've got a force there and a force here, right? What does that mean when the member is in tension? Well, if you take a look at the end here, where that member is pinned to the wall, right? What that means is you have this member, and the pin itself, the pin that sits in that hole and the pin that sits in this hole are actually applying the tensile forces on that member. Right? So what does that mean? It means that if I take a look at the hole, right? At the hole there. Take a look at this hole. That pin that sits in that hole is pushing against that hole. All right? So now let's blow up that hole. That pin that sits here is pushing against it. So basically there's a bunch of forces from the pin pushing against the hole. Now, why is it only half the hole? Well, because if the pin is being pushed that way, right, then it's going to push right against that half a hole here. The other half, you actually get a little bit of a tiny bit of gap, right? So there is actually no contact between the pin and that second half of the hole, right? So all the pressure from the pin pushing on that hole is on this left side, right? So there's obviously a normal stress because these forces are all acting perpendicular to that semicircular arc, right? So how do you calculate that stress? Well, one thing you can do, right, the hard way to do it is you know that you've got a bunch of forces, right? And you've had, so what you can do is you could integrate the forces over that whole surface, that half a cylinder of surface, right? You could take, integrate the forces over that whole surface, and you get the total force that's pushing against that semi-cylindrical surface, right? And then you just take that total force divided by the area, right? That area of that semicircular, semi-cylindrical area, right? And that will give you your sigma, your stress, okay? That's obviously going to be a lot of work, right? Trying to integrate to find that total force. What actually ends up happening mathematically, right, is there's no need for that integration, okay? What ends up happening is you will get the exact same result if you were to take, okay, the projected area. That's simply this area, that area here. The projected area now is a very simple rectangle, right? And the area is simply the thickness of your member times the diameter of that hole, okay? And now your sigma is the the P, right, the tensile or the compressive force on that member divided by TD. That's what we call a bearing stress, okay? Because that semicircular, that semi-cylindrical area is what we call a bearing surface, right? Because bearings usually have cylinders spinning within them, right, or pushing against them, okay? So it's just a bearing surface. All right, so that's a bearing stress. Now, how important is this? Well, to be perfectly honest, right, this is not used very often, okay? And this is probably the only chapter where you're going to see this, okay? The rest of this course, you will never see this again, okay? But, you know, this is something to be aware of, right? It's another form of a normal stress that you might run into at some point in your career as an engineer. Okay, so that's the bearing stress. And the rest of the next few slides here basically delve into a lot more detail of that frame problem that you were given at the very beginning. Okay, so what's going to happen now is the book says, well, we could throw a lot more detail now into the structure, right? What we can say is that at joint C, right, we were originally told that it was a pin joint, right? But we can now look at exactly how it's pinned. So basically, there's a tab that's attached to the wall, right? And then the end of that member BC is flattened, so you have two tabs that are sitting against each other. You drill a hole through both tabs, and you put a pin through it, right? And you know that member BC is in tension, so we can look at that pin joint now, right? Take a look at that pin joint, and try and determine what else is going to happen within this joint, okay? So can everybody see that there's going to be a shearing stress, right, on that pin, right? Because the tab and the member BC are being pulled in opposite directions, right? So there's that shearing that goes on at the junction on the pin. So you could find the shearing stress, right, on that pin. And what does that allow you to do? Well, that lets you kind of choose an appropriate material to make that pin out of, right? What else goes on that at that pin joint there? Well, that pin, right, is being pulled or pushed against the holes. So there's a bearing stress, right, on that pin and on those holes as well. So you could calculate that, right? I'm not going to go into the details here, right? You can look at the rest of the slides in more detail if you want, or look at your textbook, right? Looking at joint A, right, you see something that's similar, right, but there's a slight difference. So at A, you now have kind of a U bracket, right, that's attached to the wall, and then your member actually sits in between that U bracket, right, sits in between there, and then you put a pin through the whole thing, okay? So can everybody see now that that pin is going to be under double shear, right? So you know how to calculate that now. And then, of course, you have bearing stresses, right, on the pin as well as on those holes, okay? And then you have something very similar that goes on at joint B, right? Joint B is more complicated because there's an applied force of 30 kilonewtons pulling down, right? But again, it's all pretty much the same thing, right? You have bearing stresses and shearing stresses on the pin and on those holes. All right, so take a look at those details on your own if you're up to it, right? Otherwise, just it's not even necessary, right? I want you to get used to this idea of a normal stress, right? Get used to the idea of a shearing stress, and then another important thing, of course, is those different variations of the design problem that I talked about. Okay, so let me skip off these. These are all the details. so the next thing that we're going to talk about, all right, this is a new topic now. We've been talking when it comes to normal stresses, right, only about tensile and compressive forces, right? We were basically looking more or less at members that were very similar to the members in a truss, right, that were only in tension or compression. And that is perfectly fine, right? But even in a simple case like that, right, there are different ways of looking at your member, right? So this is a very interesting situation here, and perhaps I'm better off by drawing it. Okay, so we have this this long rectangular member, right, and it's being pulled in tension. So I apply tensile forces on both ends. Okay, so the simplest way, or the most obvious way of looking at this, right, is to say that, well, I know there's a sigma, a normal stress on this member that's equal to P over A, right, where P is this force that I'm applying on the two ends, okay, and A is the cross-sectional area, right, that cross-sectional area. However, right, what if I were to look at the cross-section a little differently? Instead of looking at it as that simple rectangular cross-section like that, right? Maybe I want to look at it as an inclined plane. All right, let me redraw that for you. Now I look at that plane, right? So I know there are these forces P acting on it still, right? And now I have this plane, okay? So one thing we do know, right, is that this force P, this internal force P, acts throughout this whole member, right? So even at that inclined plane, there's still a force P, right, pulling towards the right and towards the left, okay? But now my area is at an incline, okay? And this is at some angle theta. What are the stresses on this incline now? Well, there are two kinds of stresses that we talked about, right? We know there's a stress that's perpendicular to a cross-section. That means it's due to that component of force P. And we know that there's a stress that's parallel to the plane of a cross-section, right? That's your shear stress. So now you have this. So what are these two forces? Well, you know that they're components of this force P, right? This is, if that's angle theta, then this is angle theta, right? That's angle theta. So this is P sine theta. This is P cosine theta, right? And that means on that plane, on this inclined plane, you have sigma equal to P sine theta over this area. Is that area equal to the original area that we were looking at? No, right? That's a different area. But you also have a tau equal to P cosine theta over area, right? And how do I calculate that area? Well, excuse me. If this original length here was base, right, and this were height, and you look at this new area, right, this new area still has base B, right, but you don't use the height anymore. Now you have to use this distance, right, where this was theta, So what is h? H is equal to, let's call this new length here a, right? H is a sine theta. So a is h over sine theta. Right? So what is this area here? This area is equal to is equal to b h over sine theta. Okay? BH over sine theta. That's my new area, right? So when you calculate those stresses, you're going to have that P sine theta over BH sine theta, and you have P cosine theta over BH over sine theta, and so on. Okay? So that's what all of this is going through, right? So what is the whole point behind this? It's to tell you that stress is a matter of perspective, okay? Even though we said that, you know, you have normal and tensile stresses and a shear stress, right? That's all a matter of perspective. And what I mean by that is this, right? When you have a well-defined part, you know, it's long and thin, right? And it happens to be pulled in tension or compression, then yes, right? You're going to take a look at this as if all it has is a normal stress acting on it. But what if you start having complicated structures, right? Or what if you start having forces now that are acting in different directions? So one example would be like if you had this structure, right? And now instead of pulling in tension or compression, maybe I apply a force at some angle. Right? Now how do I calculate the stresses on this? Well, I could definitely break that force down into components, right? And now I could calculate a normal stress and a shear stress, right? So that's very similar to what we just did, but let me make it even more difficult now. What if I have some kind of random shape, random structure, and it's got, you know, a few forces acting on it, right? How do I calculate the stresses on something like this, right? So it totally becomes a matter of perspective, right? How do I define what direction is tensile, what direction is compressive, right? What's shear in a case like this, right? It becomes very subjective, okay? There's no right or wrong way of looking at the stresses on a structure like this now, okay? So this is what we're gonna get into, right? So let me kind of take a step back here, right? And say that when we talk about stresses on a structure, right? There are two ways of looking at it. If it's a very simple structure, like we've been looking at, right? These long, thin members that are just pulled in tension or compression, then it's pretty obvious how you're going to look at the stresses, right? You define your stresses as being tensile or compressive, right? And if you have shear, then you go ahead and take a look at the forces that are parallel to your cross-section, right? So that's one way of looking at it. Another way of looking at your stresses is to look at stresses at particular points, okay? So even if I have a very simple structure like this, right, that's pulled in tension, I could choose to pick a single point on this structure and then try and look at what the stresses are at that point, okay? Now, how is this going to work? Well, in order to do this now, I've got to define a coordinate system. Once I pick a point on here, then basically I just focus on that point. I forget about the rest of that structure, right? The rest of the structure doesn't even come into the picture anymore. I look at that single point, and what that means is I have to define a coordinate system, right? And usually, right, we do something like, well, I'm going to make the horizontal x, I make the vertical y, I make the axis that comes perpendicular out of this, make it z, right? And now my point is here, and I need to define what the stresses are at that point, okay? So when you do that, right, now you no longer just have a single sigma value and a sigma tau value, because this point, right, might be pulled in tension. And well, in our case, right, we know that this point is being pulled in tension in the x direction, right? So if you were to define your x-axis this way and your y-axis upwards and your z-axis out of the page, then all you have in this case is sigma x, right? And there's no tau, right? There's no sigma y, no sigma z. All you have is sigma x, right? But what if we were to go ahead and choose a different coordinate system, right? You've got this point, and now maybe I make that my, sorry, let me redraw it, okay? So I've got this structure being pulled that way. I've got this point that I'm looking at, right? But now maybe I look at that as my x-axis, that's my y-axis, and that's my z-axis, right? What stresses do I have now? Well, if you think about this, right? Tension means that something is being stretched. Compression means that it's being shortened, right? And shear meaning that it's being basically ripped apart, if you will, right? So what's going on now if I look at it like this? Well, I know that this point is being stretched horizontally, right? This way and that way. But that's not any of my coordinate directions. That's not x, y, or z, right? So what that means is that if I look at x, right, this point is actually being pulled a little bit in the x direction. So there's some sigma x there, right? It's being pulled a little bit in the y direction as well, right? And it might be pulled a little bit in the z direction, although it depends on how I'm orienting this. If x and y are in plane, right, are in the plane of, or in the same plane as this, then there might be no sigma z, right? However, there's still going to be some tau, okay? There's going to be some shearing that goes on here, right? So it's a matter of how you set up your coordinate system, right? Even in a very simple case like this, if I set up my coordinate system incorrectly, if you will, or in not the best way possible, then I end up with a bunch of different stresses, okay? But if I set it up correctly, meaning I just make one of my coordinate directions the same direction as the direction that the forces are being applied, then I have just one stress value, right? So that brings me back to that general case, right? If I have a situation where I have some weird structure, some random structure, and there are forces being applied in all directions, right? And I take a point on this structure, and I want to know what the stresses are at this point, right? How do I determine that? Well, it now becomes pretty arbitrary how I set up my coordinate system, right? I could choose that to be the x-axis, that to be the y-axis, that to be the z-axis, or I could choose any coordinate system that I want, right? And what that means is I'm going to have a bunch of different stress values, okay? So this is what we call a general state of stress in mechanics of materials, all right? And all this really means is that we're picking a point on our structure, right, and trying to determine what the stresses are at that point. So let me go back to my drawing, right? So I pick a point on this structure. I want to know what the stresses are at that point, and I first need to define a coordinate system, right? And now I've got to go and try and figure out what all the stresses are. Now, don't worry about how you're going to actually calculate these stresses, right? We'll get into that. And there actually is a way that you can measure, if you will, stresses, right? But we're talking about now how you represent those stresses. Okay? So let's take a step back here and look at our definitions, right? We know that as far as stresses go, we've got normal stresses and shear stresses, right? A normal stress always acts perpendicular to a surface, and a shear stress always acts in the plane of a surface, right? Now, the other thing that we want to kind of make use of is our standard Cartesian coordinate system, right? It's a very nice simple system because you have three axes that are all mutually perpendicular, right? Which makes things easy, right? When your axes are 90 degrees apart, then you can make use of trigonometry, right? And things are just much easier to work with, okay? So with all of that in mind, right, when we look at the stress at a single point, okay, what we need to do is come up with a way to visualize that point such that our stresses are always just in our coordinate directions, x, y, and z, okay? And the best way to do that, okay, is to take a look at a point or to represent a point, right, on an object as a cube. So why a cube? Because if you look at your cube, right, every single edge of your cube, right, can be made to coincide with one of your coordinate axes, right? Meaning, if I define my cube like this, then I can very easily make that my x-axis, make that my y-axis, and that my z-axis. Okay, and excuse me. And what that means is on this cube, I've got 6 different faces, right? And if I have forces that are acting perpendicular to each of those faces, right, those forces end up giving me stresses in the x, y, or z directions. Right? Does that make sense? Now, so keep in mind that this is just a single point on my object, right? So it's a tiny, tiny cube. So think about what happens here. If this cube is being stretched in the x direction, what does that mean? It means I've got sigma, right, or normal stress in the x direction, right? If this cube is stretched in the y direction, what does that mean? It means I've got sigma sub y acting on those top and bottom faces, right? What if this cube is being compressed or stretched in that z direction? It means I've got sigma z, right? And you obviously can't see the one on the back, but it's there, okay? So think about what this really means. It means if I take a cube, right, and I submerge it in water, right? You put it in a bucket of water, then that water pressure pushes equally, or more or less equally, on all 6 faces of the cube, right? And that cube is going to end up shrinking, right? That means it gets compressed in the x, the y, and the z directions. And basically it's got stresses. It's going to have compressive stresses in the x, y, and z directions, right? What if I go ahead and try to shear it? Like if I try to push that top surface towards the right, and then I try to push the bottom surface towards the left. That gives me a shear, right? That's basically trying to rip this cube apart, okay? So I could have a shear stress now in that direction, okay? Likewise, I could try to shear this top surface towards the front, right? I could try to shear this surface up. I could try to shear it to the right. I can try to shear this up, shear this left. Now, why 2 shears on each face? Well, keep in mind that we want our stresses to coincide with our coordinate directions, right? So on each face, right, how many coordinate directions do I have in the plane of that face? Like on this top face, I want a stress that's in the x direction and one in the z direction, right? I can't have one in the y direction because that's my normal direction. I already have my sigma y there, right? Likewise, on this right face, right, on this face on the right, right, what I want is a shear stress that coincides with my y direction, and I want a shear stress that coincides with my z direction. There's none in the x direction because that would be my sigma x, right? So now what you have is you have 6 faces. Each face has a normal stress and 2 shear stresses, okay? And this is what we refer to as a general state of stress. Okay. A general state of stress basically then in mechanics of materials is you represent a point on a part by a cube, right? And then there are 3 stresses on each face of that cube, okay? There's a normal stress and 2 shear stresses. Now, the 3 normal stresses are simple, right? Sigma x, sigma sub y, and sigma sub z. How about the shear stresses? How do we designate these different shear stresses? Okay, so let me go ahead and redraw this. All right, so let's start with this face. Okay, this was sigma x, right? So here's how we're going to do this. If I take a look at this stress, right? This shear stress is in the y direction, right? And it is in what I'm going to call the x face. So what is the x face? The x face, right, is the face that's perpendicular to the x-axis. Okay, so this is what I'm going to call tau xy. It's the shear stress that's on the x face, right, in the y direction. This shear stress is what I'm going to call tau xz, right? It's in the x face in the z direction. Let's go to the top, right? This is sigma y. This is tau y face, right? Because this top face is perpendicular to the y-axis. And then in the x direction, right? I'm going to have a shear stress going towards the z direction. That's my tau yz. Okay? Then I'm going to go to this front face. I have my sigma z. Right? Notice I'm drawing all my sigmas as being tensile. Right? It doesn't matter. They could be compressive as well. This, right, is tau z face y direction. This is tau z face x direction. Okay? And then I left out the other 3 faces, but you could kind of imagine the same things going on in those 3 faces. All right? So how many total stresses do you have at a point? You've got 3 stresses on each face, right? And 6 faces. So that's 18 different stress values. 18 stress values. 18 stresses at a point, right? There are 6 sigmas and 12 taus. So do you actually have 18 different stress values that you need to worry about at a single point on any structure? Right? That seems a bit excessive, and it is. Okay, so keep in mind that mechanics of materials is essentially an extension of statics. Right? So what that means is everything we look at is in static equilibrium. And the equations of static equilibrium still have to hold true, right? So if you think back to your 3D equations of equilibrium, you need to have sum of forces in the x, the y, and the z directions are equal to 0, right? That's 3 equations. And then you need sum of moments about the x, the y, and the z axes equal to 0. That gives you 3 more equations, right? So you've got 6 equations of equilibrium that you must satisfy. Okay, and what you can do is you could actually apply those 6 equations of equilibrium to this cube, right? And what that means, okay, if you were to actually go and do the math. Now, obviously, these are stresses or pressures, but they can be converted to forces, right, to apply your equilibrium equation. You simply assume a unit area. Assume that this cube has sides of 1, right? So all your areas are equal to 1, and then you just multiply all your stresses by the areas to turn them into forces, right? So that's very easy to do. Then you apply your force equilibrium equations and your moment equilibrium equations. And what you're going to find, okay, is this. This sigma x, right, on the right face must be equal and opposite to the sigma x on the left face. And actually, they're opposite in direction, right, but they're equal in magnitude and in sign because they will both be either in tension or in compression, right? So there's only one sigma x, okay? Even though there's a sigma x on 2 faces, right? They're the same value, so it's actually one sigma x value. Same thing for your sigma y's, right? Same thing for your sigma z's. So even though we say that there are a total of 6 sigmas on a cube, there are only 3 actual values, okay? How about your taus? Well, those equations of equilibrium basically tell you that tau xy equal to tau yx, okay? That has to be true. And likewise, tau yz is equal to tau zy, and then tau xz is equal to tau zx, okay? And then this tau xy on this right face has to be equal to the tau xy on the opposite face, right? And once you apply all of that, okay, what you end up with is you actually have only 3 stress, not 3 stress values, but you have 3 sigma values and 3 tau values, right, for a total of 6 stress values at a single point in 3D, okay? And those values are sigma x, sigma y, sigma z, right? Tau xy or tau yx, right? Tau yz or tau zy, and tau xz or tau zx, okay? These are 6 distinct stress values at a single point, okay? So it's not 18, it's just 6, okay? So what do we do with these 6 stress values, right? The comparison that I want you to make, right, or the analogy that I want you to make is it's very similar to a force in 3D, okay? Stresses can be looked at in a very similar way to how you look at forces in 3D, right? So let's say I don't want to do that yet. So let's say I have a force in 3D, right? It's acting in some direction, right? Depending on how I define my coordinate system, right? If I were to make that x, make that y, make that z, depending on how I define it, right? I know that this force can be broken up into an x component, a y component, right? And a z component, right? Right? That kind of represent the sides of a cube, right? Now, depending on how I set up my coordinate system, right? So there's my force, but now maybe I make this my x-axis, and that my y-axis, and that's my z-axis. I end up with 3 different components, x, y, and z, of this force, right? Do these 3 components have the same values as the previous 3 components? No, right? Because I chose two completely different coordinate systems. But do the first three values and the second three values represent that same force? And the answer, of course, is yes, right? It's all the same force that I've broken up into components in two different ways, right? So they're equivalent. So when it comes to stresses, okay, it's the same thing. Let's say I've got this structure, right? I've got a structure, and then I pick a point, right? And I'm trying to look at the stresses on this point. Depending on how I choose my coordinate system, right? If I choose x, y, z, then I'm going to get 6 distinct values for sigma x, sigma y, sigma z, right? Tau xy, tau yz, tau xz, right? Then if I choose a different set of coordinate axes, and I look at the stresses in this new coordinate system, I'm going to get 6 different values of those stresses, right? But do the two sets of 6 stress values represent the same thing? Yes, right? They're all representing the stress at that single point, okay? So how do I go from one coordinate system to the other, right? That's a topic for chapter 7, which we'll get into, right? But for now, kind of keep in mind that this is how we represent stresses in 3D, right? 6 different stress values, all right? So that's your general state of stress. Okay. If this seems a bit much, don't worry too much about this. Right. We're going to delve a lot more into this as we go along here. Right. And in fact, it's very rare that we look at stresses in 3D. Okay. This is the most general situation. But mechanics of materials, okay, believe it or not, it's mostly a two-dimensional type of analysis, okay? So that makes things a little easier for us, okay? All right, so I'm going to move on to the next topic here, okay, which is factor of safety. So if you think back to some of the discussion that we had a little bit earlier, right, when we were talking about the design problems, and I said that a lot of times when we choose materials, we choose a material based on its ultimate stress, right, or its ultimate strength. And that's perfectly fine, right? But a lot of times that's it's a little risky to simply rely on the ultimate stress, right? So let me repeat some of the analysis that we had done, right, earlier. Right? Remember when we were talking about designing a column, right? And let me just use that last case, right? Which is the situation where you're designing this product, right? And you know you want to make it out of steel, and you know you want the diameter to be 0.5 meters, right? And you have to tell the customer what the largest force is that they could apply to this column that you're going to sell them, right? And I had said that the way we're going to do this is you basically look at what stress steel is going to break at. So you said, we looked it up, right? Sigma ultimate was, what did we say, 324 MPAs, right? And then we said we're going to set that sigma ultimate equal to P over A and solve for P, right? So why is this risky? Well, because if you sell this to the customer and you tell them, right, you could apply this much P, right, and they actually go ahead and apply that much, right, what are they loading this structure right up to? They're loading it right up to the breaking point, okay? And that would be fine if you are absolutely certain that the steel that you've used is fine, right? There were no defects in it. It was made correctly. It was heat treated correctly, right? But what if someone had made a mistake? And this particular piece of steel that you used is weaker than what the specifications say. You would be in trouble if the customer actually tried and load this part right up to that breaking point, right? So out in the real world, we would never simply just rely on that ultimate value, okay? We use what's known as a factor of safety. And a factor of safety is exactly that, right? It's for safety. It's to make sure that your parts are never loaded right up to the breaking point. All right, so the way it's usually defined, okay, is we take an ultimate stress and divide it by what we call an allowable stress. Okay, so an allowable stress, and that's what we define as a factor of safety. Okay, so sigma sub u for ultimate divided by sigma sub ALL for allowable. Okay, that's the terminology and the notation that we use, right? And that's referred to as a factor of safety, or FS. Now, what are typical values of factor of safety? Well, that all depends, right? It depends on how critical the structure that you're designing is, right? And whether lives are going to be at stake. Okay, so what I mean by that is, if you're designing something that's very important, that's going to be where people's safety and livelihood depend on the structure, then you want to use a large factor of safety, right? If you're designing something where a failure is not going to be anything catastrophic, then usually you could use a lower factor of safety, right? So bridges, right, buildings, right, when you design parts of those types of structures, then you have large factors of safety, right? When you design parts for like airplanes, obviously factors of safety are pretty high, right? But when you design very simple things like a table, right, maybe a chair, then you could usually get away with lower factors of safety, okay? So a typical value in civil engineering is somewhere right around 2. Okay, usually a factor of safety of 2 is pretty adequate. Okay, and that's just kind of a ballpark figure. Okay, now factor of safety is used, right? Usually, in a lot of problems, you're actually given the allowable stress. Okay, and that means a factor of safety has already been specified, right? And in the problem, they've already taken the ultimate stress and divided it by the factor of safety, right? And to come up with an allowable stress. All right, so we'll get into problems where we deal with factor of safety as we go along, right, in this course. But for now, okay, make sure you're comfortable with this definition. Okay, usually, again, let me note that down. Usually, okay, right around 2. Okay, it's a very typical value. All right. So now, why is a factor of safety required, right? I already kind of mentioned a little bit why, but let's go and make a larger or more comprehensive list of why factors of safety are even required in the first place. All right, so. Okay, first is you might have uncertainty in material properties, right? And that was what we were talking about earlier, right? You buy a batch of steel, right, or a batch of any material, and you could usually be fairly certain that that batch of material has an ultimate strength that's equal to whatever's listed on the tables that you use, right? But sometimes a mistake was made in heat treatment, right? Sometimes, there are air bubbles maybe, right, in your material somewhere that's going to weaken it, right? Whatever it is, whatever the case may be, the batch of material you get might be inferior to what is expected, right? In that case, if you use what's listed, right, in your tables, then your actual material is going to be weaker than what's listed, right? So you want to make sure that you account for that uncertainty, right? So the way to do that is to use a factor of safety, because you can't really test every batch of material that you get in, okay? Next, uncertainty of loadings. This is basically like you sell this product to a customer, you tell them what the largest load they could apply is, they could apply, right? But what if they go ahead and exceed it without even knowing it, right? You want to make sure that when a customer unknowingly exceeds the rating of your product, that that your product still doesn't fail, right? So the way to do that, of course, is you tell the customer that they can load it up to a certain point, when in fact you know that your material can actually withstand more than what you tell the customer, okay? Uncertainty of analyses. That's like, what if someone made a mistake in a calculation, right? It might be like a 10% error in a calculation, right? But if you want to make sure that that doesn't lead to a failure, then you just incorporate a factor of safety, okay? Number of loading cycles, that's important, all right, as we'll get into next lecture. Basically, when you load a part over and over, you load it, unload it, load it, and unload it over and over, a lot of times that could start to weaken or degrade the structure, right? So you want to make sure that even after repeated loadings and unloadings, that your structure can still withstand whatever you tell your customer it's able to withstand, okay? Uncertainty of types of failure, you just want to make sure that your material can withstand, or your product can withstand any type of failure that could possibly happen. Right? And the way to do that, again, is to put in a factor of safety. Okay. Next, maintenance. Right? When you design a bridge, right, this is very important. When you design a bridge, right, you know that that bridge can withstand a certain amount of load, but that's assuming that that bridge stays in perfect condition, right? We know that bridges will start to rust, right? The metal parts start to rust. Water could get into concrete, right? You know, over the course of many years, bridges do start to degrade and get weaker and weaker, right? And what's usually assumed is that government, right, especially your local government, will go ahead and do the required maintenance, right? But of course, these days, due to budgets and things like that, sometimes a lot of maintenance is skipped, right? And bridges do start to deteriorate then because they're not maintained very well, okay? So if you put in a factor of safety that's large enough, then you could cover a lot of that deterioration, okay? And of course, there have been stories, all right? We know that these things happen where bridges collapse, right? Usually due to age and lack of maintenance, okay? And let me see, what else? I mean, you know, you kind of get the idea, right, of why factors of safety are needed. So another important thing is where that structure is going to be used, right? If you design a structure and there's some possibility that your customer, for instance, might take this structure and just use it in seawater, in a saltwater environment, then you know salt water is going to cause degradation, right? It's going to cause corrosion to your part, right? So having a factor of safety would help account for that as well. Okay, so that's basically factor of safety. Okay, and I am going to end this lecture right here then. Okay, so just to recap, right, what are some of the important things that we talked about today? Well, most important, of course, is this idea of a normal stress. Okay, it's very similar to a pressure, except it has a direction, right? Then we talked a little bit about an average shear stress, right? So that's a stress that's parallel to a cross section, okay? And then we basically moved on to We moved on to a general state of stress, right? Keep in mind that in 3D, okay, we look at a point as being a cube, right, with 6 faces, of course, 18 total stresses, but actually just 6 different stress values, okay, due to equilibrium. And then, of course, we talked about a factor of safety, okay, and why we need a factor of safety. All right, so I will go ahead and end this lecture right here, okay. We will pick it up next time with chapter 2 in the textbook and continue our discussion of normal stresses and shear stresses, okay. So with that, all right, let me sign off and look for my next lecture within the next few days, okay?